This talk is the lowest technology talk from all of yours, just so you know. So it's very, very basic, and it has to do with environmental optics. So the idea of using optics to study the environment. And I hope you'll find some relationship to other things you guys are doing. So why do we use optics in general for the ocean-wide oceanographers care about the optical properties of the ocean? It's primarily for several reasons. One is the color of the ocean is seen from space, from satellites, provide us the highest resolution data on biological processes in the ocean. We have on the order of 100 research vessels in the world. And we have an ocean that covers 70% of the planet. There's no way this is sufficient to provide us information about what happens in the ocean. And since the discovery that biology, primarily biology, but also sediment processes in land-ocean interaction affect color strongly, people have started to use that color as seen from satellite as something extremely useful. And currently, there's also approach to use polarization from space and active sensors like LiDAR on satellites. Another application, a very important application that optical properties are used is as proxies for materials in the ocean. Anything that interacts with light in a variety of ways can then be used to develop a sensor that senses that thing in the water. And now we have a lot of robotic platforms with optical sensors on them going up and down around the world, sensing materials we're interested to, again, in order to study the environment. It can be anything from pH and oxygen, using optodes, to things that measure directly optical properties like fluorescence and absorption, and I'll get there. And finally, we've been coming into an epoch where we use automated microscopes to study the marine environment, which provide us a huge throughput of organisms, and I'll get to that in the end. So how does ocean color work? 90% of the signal actually that you're measuring from a satellite that was reflected by the atmosphere and ocean actually come from the atmosphere, as well as from glint, which is simply the reflection at the ocean surface, and from bubbles and breaking waves. So we need one of the hardest tasks that we have to do, we as my community of oceanographer interested in ocean color, is to remove the effect of the atmosphere, and extremely accurately in order to say something about what's happening in the water. And that's a big activity I'm not going to talk about at all. So what does the signal that we see in the satellite refer to? And I have a bunch of, I don't know if you can see the camera, but if you put it on the camera, I can show you what I'm talking about. So, and many of you, of course, know it. But when I talk about absorption, I mean the fact that if I have a red light and water that are green, very little of it will propagate through, as the red will be absorbed. However, the green is going to go through. So the color you see from space is first what's not absorbed. The signal also responds to scattering. So for that, I'm adding to the same water some scattering agent, and you can see that laser because I'm now shining into scattering to the side because there's some sediment or phytoplankton that scatter light in it. And finally, from space, we can see a signal that's only from phytoplankton, which is fluorescent. So I'm using here a blue laser shined into a beaker full of chlorophyll fixed in acetone, and you can see red light emitted out of it. There was no red in the laser. It's absorbed in the blue and emitted in the red. And this is, as a colleague of mine say, the only signal we measure from space that we know come from microorganisms in the ocean, organisms that are on the order of a micron, which are phytoplankton. Okay, so then with this signal, we can see the color, which is what you have on the left, the true color. A lot of it is affected by the atmosphere. You can see clouds and other things. And then we analyze the signal coming up and we divide into what we call products. Product might be the total particle, TSM is total suspended material in the water. We might get phytoplankton out of it, or which we quantify by chlorophyll A, and we can have information about dissolved organic. This dissolved organic is basically what you have in tea. It's material that is organically derived, and it's it's not in particulate form, just like your tea bag, what's coming out of your tea bag at home. So this is the approach with respect to remote sensing, and this is why NASA and many other, and ESA and other space agencies invest in this science. And then there's the use of optical quantities as proxies. So let's say we want to know quantity X, but we most often cannot measure it. This is even true for temperature. We measure temperature in the ocean by measuring resistance of a material that change resistant as function of temperature. So the same happens with optical techniques. As you know, we want to measure X, we cannot measure it directly, so we measure Y, which is a function of X, and then we invert that relationship to get the proxy. So we also, with temperature in space, we measure it as a black body radiation, not directly temperature, which is the kinetic energy of molecules. So what can we do with proxies? We can do directly things like concentration of particulate material, sediment, fiber particle. We can do dissolved material, the tea-like stuff. We can even do nutrients by using UV spectroscopy, like nitrate, oxygen, pH optodes, and there's a variety of other things that we can get. And even by getting an index of refraction, we can get information about salinity, because the index of refraction of water is driven by salinity, temperature, and pressure. Temperature and pressures are easy to measure. Salinity is hard. So anything that gets us. So these sensors are put on a variety of, we deploy them from research vessels, but as I said, there's very few of them. But we have these robotics tools that are sampling the ocean. There's thousands of them. The French are really good also in putting them on organisms, as you can see the seal there or in the middle. And those are cruising around the world ocean, sending data through satellites that then feed models and provide us critical information about ocean health and distribution of materials throughout the water column and the surface. And now I'm gonna end with these automated microscope that I talked to you about. The relatively new commercial sensor that we're using, there's others. These are relatively wide utility right now. The one on the left is from Hydro Optics, which is a French company. It's called the Underwater Video Profiler. It illuminates a liter of water, and with a camera on top, basically gets the number of pixels associated with particles in each of these images. On the left, we have the imaging flow cytobot from Laclane's in the US, which can be put on a mooring and sips 5 ml of water every 25 minutes, and then one by one run them in front of a camera that is triggered by a laser, and then an image is taken. Both are for very different size of particles. You're going to see them here. The IFCB, the imaging flow cytobot, is for particles from 5 to 200 micron, triggered with fluorescence or with scattering. You can see the imaging on the right. And typically we come back from a cruise with 1 million images just from that instrument that we put in inline, and continuously, wherever the boat goes, we collect data with. We have this type of instrument on the French boat Tara that's currently cruising around Europe, soon to arrive to Greece. The UVP is an instrument that's put typically on the CTD, which is a rosette. It's a set of instruments that are connected to a winch, and they go down through the water column, taking images. You can see the images here on the right-hand side of a variety of organisms. And typically we come back from a cruise with order 10,000, several tens of thousands of images. And of course, we cannot, on our own, take these particles and divide them into boxes. Here I give you an example. So AI is deployed, and the classifications are getting better and better. Here I'm showing you an example of IFCB data taken with Tara up. Something here is not in the right. These dots should be up. These dots should be right of the, I don't know how that moved, but anyways, 3 different places along the Brazilian coast. This is a leg of Tara from Brazil into Argentina I was on. And you can see in 3 different places, very different distribution of phytoplankton. On the left, we have a lot of what is called diatoms, siliceous organism. They form chains. This is all from surface. The moment we go to the deeper ocean, much less particle. That's in the Brazilian current. And finally, when we come back, we see a lot of these round dinoflagellate dominating the larger of the particle. This is kind of mosaic we get every 25 minutes. And what's interesting is as we get these data in quasi real time, every 25 minutes we get a generation of this mosaic, we can use them to tell the captain where to stop to then deploy a package of sensors, deeper, more technology that requires us to stay in one spot and sample for a whole variety of other properties. So this is extremely useful for us to study the ocean. So to summarize, optical technologies, both passive and active, provide key measurements to study the ocean and organism within them. The market for optical sensor has been expanding as people are deploying it in aquaculture and in a variety of ways by which they want to monitor ocean health. And as ocean health is becoming a subject of wider public interest, more engineers and physicists are joining in devising sensors that allow us to say more about what's in the ocean, how it behaves, and what it's doing. And I'll stop there. Thank you very much.